All right, let's take a look at some example problems that use this standing wave equation, this idea of harmonics. So the first one we'll do won't be musical at all. We'll look at just maybe flipping a clothesline around with your hand, and maybe you've had a chance to do this in your backyard before. Let's say you're flipping your clothesline and you create waves that travel, this is pretty slow, 0.72 meters per second. By experiment, you find several frequencies at which you can oscillate your end of the line so that a light clothespin 45 centimeters from the post doesn't move. What are those frequencies? So, wow, let's draw a picture of what this looks like. So we'll draw some kind of a post here. And we got on you, you're going to be wiggling this clothesline. There's nothing better to do here. Up and down. And there's going to be a clothespin. It's like about 45 centimeters from the post. And this clothespin is not moving. So that means that the clothespin has to be at a node, a place that doesn't go up and down. Now the place where it's tied to the pole also has to be a node, and wherever it's connected to your hand has to be a node as well. So we'll have nodes here. And there are a lot of different ways this could look, but the simplest way it could look, because nodes and antinodes alternate, is that there's just an antinode in between. So I can draw something kind of like this. And I don't know how many times this thing goes up and down. It might go up and down a bunch of times here. But I do know that this spacing right here is the spacing between two nodes. Okay. So the key for this then is recognizing that in this case, if this is the distance between two nodes, we have just the crest of a wave or just the trough of a wave. So we need to be able to look at this picture. We need to recognize that we're seeing half of a wave. Remember, an entire wave is both a crest and a trough, and we're seeing, say, just the crest, which would be half the wave, or just the trough, which would be half the wave. So this spot, this 45 centimeters, or 0.45 meters, is going to be equal to half of a wave, lambda over 2, 1/2 of a wavelength. So this allows me to figure out what my wavelength is. Multiply 0.45 by 2. The wavelength right here would be 0.9 meters, or 90 centimeters. The length of an entire wave would be both the crest and the trough. Okay. So now I know this. The other given quantity is the speed of the waves in the string, 0.72 meters per second. So just based on the picture, being able to recognize my half wavelength, I've got everything I need. I can figure out what frequency I'm vibrating this with, because I know there's a relationship for all waves between speed, frequency, and wavelength, v equals f lambda. So I can plug the numbers in here. 0.72 meters per second equals f times 0.9 meters. So 0.72 divided by 0.9. And we get one of the frequencies that I can vibrate this and keep the clothespin at rest is 0.8 hertz. That's pretty slow. Okay. So that's one of the frequencies that will produce standing waves like so. It's the slowest one that will do that, the simplest one that will do that. And what I recognize, what I can see here, I need to figure out all the frequencies, as what are those frequencies plural. There are some higher frequencies as well. And so you can see what those higher frequencies will look like if we were to kind of zoom in on this here and take a closer look at this region. Kind of redraw this here, say my clothespin and post right here. I don't just have to have a node at either end. I could have any number of nodes in between. So I could, for instance, have a node in between like this. And this pattern would also keep the clothespin at rest, and this gap here would still be 45 centimeters. So it doesn't have to be half a wave, it could be a whole wave, both the trough and the crest. So this is going to fit the same harmonic pattern as my standing waves and strings. So this is going to be the simplest one that will cause this to happen. I can treat this like F1. And then I can recognize that each successive frequency is just going to be n times the fundamental. So if I double my frequency, I'll be able to fit a whole wave in rather than just half a wave. So in this case, I can put, so I have 0.8. The next one in the pattern, call that F2, is just going to be 2 times 0.8 hertz, which is 1.6 hertz. And the next one's going to be 3 times 0.8 and 4 times 0.8, so 1.6. And then F3 is going to be 3 times 0.8 is 2.4 hertz, etc. They're just going to be It'll be multiples of that fundamental. All right, let's do one that deals with music now. I don't know about you guys, but I spent a good deal of my childhood trying to get in the Guinness Book of World Records. I haven't been successful yet. But one of the ways we could do this and conceivably get in the Guinness Book of World Records is try to build the biggest of something. So I was thinking about sort of building the biggest bass fiddle, one of the deepest instruments, which would, of course, would play a very low frequency. And so let's suppose we try to build a bass fiddle that's 5 meters long. So that wouldn't even fit in our classroom. Even laying down, it might, I have to put it out in the hallway. Okay. So we have this really heavy cable, about 40 grams per meter. The lowest note the human ear can hear, there's no point in playing anything lower than that, 20 hertz. We're going to try to play that note, and we need to figure out how tight the string has to be stretched. So what I'll do is I won't try to draw the whole bass fiddle, but please don't make any baseless accusations against me here, but I will draw what that fundamental looks like, because that's going to be the note that I hear. The fundamental frequency is the main note I hear. So in other words, kind of draw in this sort of a position, since it's an upright instrument. That the string's going to be vibrating back and forth between the two ends. We know the length, in this case, is 5 meters, ridiculously long string. And we have our mass here, our 40 grams per meter. So what I'm going to do here is I'm going to try to find the tension in my string, how tight the string has to be stretched to produce this, based on the fact that I'm going to be hearing a fundamental frequency. In this case, I know the frequency, F1 of 20 hertz. So here we're going to use the equation that we derived on the previous page. The frequency of the nth harmonic is equal to n over 2L times the square root of the tension divided by the mass per length. So we really have everything we need to know in here other than the tension. So we'll plug our numbers in. So the frequency, 20 hertz. It's fundamental, so little n is going to be 1 in this case. 1 over 2L, where L is 5 meters. So 1 over 10. Square root of the tension. And then I have my mass per length, which has actually been given to me. I have the mass per length here, 40 grams per meter. Although I do have to be careful with my units. I'm going to divide this by 1,000 to get this in kilograms instead of grams. So it's 0.04 kilograms per meter. And now I'm going to get newtons of force. So this can be solved. I can, multiply both sides by 10. I can square it, multiply by 0.04, and we can find our tension. And so this bass fiddle will have to be stretched with 1,600 newtons of tension. That is a ridiculous amount of tension. It's going to be difficult for this thing to structurally hold itself up. That's about 500 pounds of force. But any looser than that, and the note's going to be too low, right? If the tension's smaller, the frequency gets smaller, and I can't hear it. So I doubt I can actually even hear 20 hertz. I'll probably have to stretch it a bit tighter than this. Okay? So the next question asks me to find the frequency and the wavelength of the second harmonic. So this isn't actually very hard. I don't even need to use the same equation again. I know what the first harmonic is, and each harmonic is just a multiple of the fundamental. So if I want to find the second harmonic, then I put 2 in for n, and I multiply it by the fundamental, which has been given to me as 20 hertz. So my fundamental is 20, my second harmonic is double that, 40 hertz. Okay, that's still pretty low. In fact, your ear probably isn't going to hear that, not very sensitive to that sound. Okay. And then we need to find our wavelength in this case. Now I could, if I wanted to, I guess I could use my speed equation, v equals f lambda, and I'd have to use this equation to find the speed of the wave in the string. What I like kind of doing is just drawing the picture. I think I can figure it out from this. My bass fiddle is 5 meters long, and my second harmonic looks something like this. It's the one that has the 2 lumps moving up and down, so that means this distance right here is 5 meters, from one end to the next. So that's an entire wave, a crest and a trough. So my wavelength is the whole length of the bass fiddle, 5 meters. Okay. The last one here on this page, number 3. What are the frequency and wavelength of the sound waves in the air when the string is vibrating at its fundamental frequency? Don't overthink it too much. If the string vibrates up and down 20 times per second, then it's going to push the air back and forth 20 times per second. So whatever frequency the string vibrates with, that's going to be the frequency of the sound wave created in the air. But the wavelength's going to be different. It's going to be way different. It's not a wave traveling along the length of the guitar, but it's a wave, or the fiddle, it's a wave traveling through the air. So we're talking about a wave of compression. So here is where I can use V equals F lambda. And I'm going to use the speed of sound, not the speed of the wave in the string, as my speed for a 20 hertz wave. So 343 divided by 20 gives me a lambda just over 17 meters. So the waves in the air are actually a whole lot longer than the waves in the string. So they're going to sound the same. They're going to be vibrating at the same rate.